looking in this set of slides is the dissociation of water and how this relates to pH. It starts on page 12 of your booklet. So we're going to be covering the dissociation of water. So basically water dissociating, splitting up into different sections. We're going to be looking at the ionic product of water, which is Kw. Be careful, we know that K is the equilibrium constant. However, when we're dealing with water, it's the ionic product of water, and there is more to it than it just being the equilibrium constant. We're going to look at how Kw and pH relate to each other, and finally we'll do some calculations of pH. Right. When we've got water in aqueous solutions, we do have an equilibrium between the water molecule and hydronium and hydroxide ions. Now, hydronium ion, that's what this H3O positive is. Okay, if we look at the left-hand side, we've got two water molecules, and they're reacting to produce a hydronium ion and a hydroxide ion. In past, you'll have seen this written as H positive and OH negative. Now, the H positive is so small, it's very, very difficult for it to exist. In our water molecules, they've both got two lone pairs of electrons. Now, what would happen is the H positive ions are attracted to the lone pairs of electrons on one of the water molecules. They'll then form a dative covalent bond with a set of lone pairs from one of the water molecules and form hydronium, your H3O positive. Okay. We can say that the hydronium ion is a hydrated proton, because that's what it is. We've taken our H positive and we've hydrated it with water. Now, shorthand representation of this is H positive. That's how you've written previously, but in advanced higher, if we're talking about water and the hydronium ion, you need to say it's H3O positive, not H positive. Our water equilibrium, it sits to the left-hand side. So we know water favours molecules. That's why you only just that's why we always know that water can conduct electricity. Okay? It is because there are some ions present. There's not a lot of ions, but there are some. And that's because it sits to the left-hand side of the equation, and we've mainly got our water molecules. As we've already said, we found out that H positive couldn't exist in aqueous solutions alone, and that was due to the size of it and also the attraction, as we said, from the water, forming a dative covalent bond to give you the hydronium ion. Ionization of water. Water is amphoteric. We are going to come back to this in the next section and go into it in more detail when we're looking at the Bronsted-Lowry theory. Okay, but what we need to know at the moment is that amphoteric means that the substance will behave as both an acid and a base. As we've already said, we know that K is a symbol for the equilibrium constant, and we know that water is in a state of equilibrium. We've got to watch, because we've been talking about the dissociation of water, Kw is the dissociation constant. It's not classed as the equilibrium constant, it's classed at dissociation. It's classed at the point at which it's splitting up into the ions. So it says there, the dissociation constant for the ionization of water is also known as the ionic product. So if you're asked for a definition of the ionic product of water, it would be that this is the dissociation constant for the ionization of water, and it's represented by Kw. We learned in the last slides that we did to do with equilibrium that the value for water, because it's a pure liquid, is 1, same as a pure solid is. Now, I know in the first lesson we did on equilibrium, we didn't know that information, and we did some calculations, but we worked out a value depending on the mole ratio and what other values we had at equilibrium. Okay, but I said to you last lesson, going forward, we must use the number 1. I didn't want you to go back and do those calculations again, because the aim of them was just to practice trying to work out the value for K. As I say, going forward, we need to use this as 1. This is important because we know from looking at our balanced equation, sorry, not our balanced equation, our equilibrium equation, we have got two water molecules on the left-hand side. So if we were to write Kw, we'd be writing the concentration of H3O positive times the concentration of OH minus over the concentration of H2O times the concentration of H2O. Now, if we put that number 1 in for both of these values on the left-hand side, 1 times 1 is 1, and what we would have is the concentration of H3O positive times the concentration of OH negative over 1. And that would mean that the equilibrium constant or dissociation constant would be Kw equals the concentration of H3O positive times the concentration of OH negative. Are you happy with that? If you aren't, please ask. Okay. Now, we know that the equilibrium constant is affected by temperature in the exact same way the ionic product of water also varies with temperature. Right. We need to know that the Kw, or the ionic product of water, at 25 degrees is approximately 1 times 10 to the 14. When we're doing most of our calculations, we're going to assume that it, unless it tells it otherwise, but we're going to assume that it's at 25 degrees C. So we're going to be using the figure 1 times 10 to the minus 14. The next bit we're looking at is a relationship between pH and the hydronium ion concentration. So if we're trying to work out the pH of a substance, what we want to do is a negative log of the concentration of the hydronium ion. Okay, if we're trying to work out the concentration of the hydronium ion, it's the inverse log of pH, negative pH, sorry, you must put that negative sign in. Okay, so the inverse log of the negative pH. And there's just a reminder at the bottom that when we've got the square brackets, that means we're talking about the concentration. So we're going back to pure water. And we know that for every molecule of water that's ionized, we will get 1 hydronium ion and 1 hydroxide ion. We also know that the concentration of the hydronium ion in moles per litre must be equal to the concentration of the hydroxide ion in moles per litre to the minus 1 for pure water. Okay, we're getting a 1-to-1 ratio in terms of the ions, therefore we're going to have a 1-to-1 ratio. Sorry, therefore the concentration is going to be equal. We also know that if we've got water or an aqueous solution with a pH value of 7, that the concentrations of both your hydronium ion and your hydroxide ion are going to be 10 to the minus 7 moles per litre to the minus 1 at 25 degrees C. This goes back to this very key point here. Okay, so Kw is approximately 1 times 10 to the 14. I said we're going to take it as being 1.1 times 10 to the 14. So it's telling us here that both of these would be 1 times 10 to the 7. So when we multiply that together, that's where our 1 times 10 to the 14 will come from. We're now bringing Kw into this. We have said that the pH is the negative log of the hydronium ion, or the concentration of the hydronium ion is the inverse log of the negative pH. We've also pointed out that if we've got water or something that's got a pH value of 7, that both the concentration of hydronium and the concentration of hydroxide will give us 10 to the minus 7. And I said when we put them together, that's where this figure of 10 to the minus 14 comes from. Okay, so if we are given a question and we are given the concentration of either the hydronium ion or the hydroxide ion, we can work out the value of the other one by using the equation of Kw equals the concentration of the hydronium ion times the concentration of the hydroxide ion. Or if we're given the pH, we can work out the pH of the other one by using the pH plus the pOH equals 14. Your pOH is your value for your alkali. Okay, there are some examples coming up that you can see this in. So we've said that the pH and the pOH, when they're added together, will give us 14. We've also said that in pure water, the concentration of the hydronium ion and the concentration of the hydroxide ion are the same, that's 1 times 10 to the minus 17, and that we can work out the pH of something knowing the concentration of the hydronium ion and taking the negative log of that. This is usually how we would do it for acids. We do need to add extra bits in for alkalis, which we'll come to shortly. We are going back to using H positive for the acids. So, if I have got a hydrochloric acid solution, which is 1 mole per litre to the minus 1, I need to use my equation of pH equals the minus log of concentration of hydrogen ions. I need to substitute the concentration that I'm given into there, and then just work out the calculation, and we'll get the answer of 0. One thing to note, this equation is at the front of the data book. Okay, it's another example here, and we've been told we've got 0.2 mole per litre hydrochloric acid. Using the same equation, and this time we're going to put 0.2 in. Please note there's an error in your book on this page. I think your book, it says 0.2 mole per litre HCl, but then in the actual example where the calculation has been done, it says 2. That should be 0.2. The answer is 0.7. Try it yourself. Okay, try both of them if you want. The answer you're looking for is 0.7 and you need 0.2. Okay. When we're calculating the pH of bases, it can be done 2 ways. It can either be done using the concentration of your hydronium ion times the concentration of your hydroxide ion equaling 10 to the minus 14. If you've got the figure for your hydronium ion, you'd put that one in, you'd rearrange it, and then you'd have your hydroxide ion equals 10 to the minus 14 divided by the hydronium ion. Alternatively, you can work out pOH if you have the concentration of the OH ion. And then once you've done that, do pH plus pOH to give you 14. As you'll be working pOH out here, you would then put the value in there. So what you would then have to do is remove this to the other side. So pH would equal 14 minus whatever value you got for pOH. There are some examples following. So this one here, we've got we're doing 0.01 moles per litre of the minus 1 of sodium hydroxide. We have our concentration of hydronium. We don't have a concentration here, but we do know that the whole thing together will give us 1 times 10 to the minus 14. So we're just going to rearrange the equation once we've put 0.01 in, and we get that our hydronium ion concentration is 1 times 10 to the minus 12. This isn't our pH, okay? This is our concentration of the hydronium ion, so we need to take it a step further. Next, what you're going to do is do the negative log of your concentration of hydronium ion. When you do that, you will get your pH, which is 12. The alternative method would have been to do the negative log of the hydronium ion and then working out the pH by doing 14 minus the pOH that you have calculated. So it's the other way of doing it. So I know that my hydroxide ion concentration is 0.01. So instead of having pH equals the minus log of H positive, I've got pOH is the minus log of hydroxide. There should be a negative sign there. Substitute in my 0.01 and I will get that the pOH is 2. So pH plus pOH is 14. Substitute my 2 in, then do my calculation, and again I get 12. Both these methods work, as you can see, because we've got the same answer. What I want you to do now is to complete the questions in the box at the top of page 14. The rest of the slides on this are just working through calculations. So I would pause the video for the moment. I'm not going to go through the answers in detail, but there are 1 or 2 things that I do want to mention. When you do A, it should be relatively straightforward. Okay. B, you've got to be careful. B, you've got to be careful because you're using sulfuric acid, which means that you have got the concentration that you have got is for 2 hydrogen ions. Okay, so please be careful with that. C, you're doing pOH. The way I've done the calculation there is by doing working out what the pOH value is and then doing 14 minus it. You can do it the other way as well. Okay, there are questions for the rest of this sheet or the rest of this book. Please, this one's worked through. Have a look at it. That would be a good move. You can try do it yourself if you want. It's up to you. And then when you've done it, have a look at the answer. What I'm saying for them all is do the first 4, check your answers. Okay, if you're not happy with the answer, question 1 is fully on the next page, or the answers on the next page. The answers are there for them. I've not worked through them. Go back, look at it. If you can't work out where you've gone wrong yourself, let me know and I will have a look at it. It's not a problem. Last one thing to note, that is not a typo. I did mean minus 0.398 for the pH, okay? We have said to you this in National 5 that we look at between 0 and 14, but it can extend either way. This is why, okay? Right. Next set of questions, you're going to be working out the concentration of the hydrogen ion rather than the pH, okay? For these ones, you are still using pH equals the negative log of the hydrogen ion concentration, but you need to rearrange it. So you're still using the same formula you've been using, but you need to rearrange it so that you've got your hydrogen ion concentration on the left-hand side and your pH on the right-hand side. Okay. For this, you're going to have to do the inverse log of the pH. Please be careful. I have missed a key bit out there when I said that, and I did it on purpose. Okay. When you're doing the inverse log, you must put a negative sign in front of the pH. Okay? It's one of the reasons why I've written it down there. You need to be very careful. It's negative pH. One thing you will note, if you forget to put your negative sign in, for some of the answers, it will be very, very similar, but you'll be out by factors of 10. Okay, so your scientific notation will be what's wrong. The answer will look right, but your scientific notation is wrong. So these ones, again, the answers are on the next sheet. One thing with these ones, if they're wrong, go back and check that you've used negative pH when you've done the inverse log. Okay, then as always, or if there's anything you're not sure about, please ask for help. These ones were more tricky. This one again is looking at sulfuric acid. Okay, it's talking about the hydrogen ion concentration and then the concentration of the acid. First bit is straightforward. You're doing exactly the same thing as what you were before. So you're doing the inverse log of the negative pH for the first bit. The second one, you've got to be careful. Okay, you're being asked to asked to calculate the concentration of the acid. Don't need to do that. And that is not the same as the concentration of your hydrogen ions, okay? Because you've got 2 H positive ions. So your hydrogen ion concentration is twice what it would be for the concentration of the acid. Please watch for things like that. If it was phosphoric acid, which is H3PO4, the hydrogen ion concentration you're calculating would be 3 times the concentration of the acid. The rest of the answers, I have put some hints down because for some of them, there are bits that you might have made mistakes going through. Okay, so the answers are there, but there are hints as well for these ones. As I've said, if you are needing any help, if you want me to look at anything, please send it my way. Also, I would put these on your notebook when you're doing them because it's easier. I can just go into the notebook and check it. Okay.